So this webinar is all about understanding basics of machine learning and trying to, so at the end of this webinar, you'll be able to understand what is machine learning, what are its different types, how do you run a proper machine learning model. There are certain nitty-gritties to each aspect of machine learning. We'll look into that in detail. We'll also see when you actually work with a company, how does machine learning model gets deployed in production and your actual customers start using it. And then we'll see some real world applications of it that are present right now, where machine learning is being employed, and a few case studies on how you can also try out a machine learning project. So this is going to be the flow of it. I'll just start. So let's start by understanding what is machine learning. Just give me a minute. Yeah, okay. So in very basic language, machine learning will provide the model the capability to learn from data. Okay, so this, if you understand in very simple terms, machine learning is a kind of computation or a kind of statistical technique where you can actually allow your machines to understand the data that you're given and make certain take it certain actions on top of that data. So you don't have to give it explicit instructions. You just have to allow the models to learn from the data. And then based on that, you can ask it to perform certain tasks. So few tasks that your machines can do based on the data is it can make predictions on top of it. It can analyze your data. It can give you results about your data as to what each aspect of the data is, where what is, just understanding your data in numerical terms. It can give you future predictions as to where this data is headed, what could be the possible results that could be generated. And it can also allow you to generate more data on top of the existing data that you have given. Now, machine learning is heavily data driven. So whenever you are building a machine learning model, you should always be aware of the fact that the data processing, the data input, the data ingestion, those are very main steps of your pipeline, and you should never let it go. Like all the models, all the algorithms that you will learn, everything can work according to its potential if you have the right amount of data and the right set of data. So the entire goal of machine learning is to learn from the data, to understand the nitty-gritties of the data, to understand what the data is all about, and then make future predictions or future generations based on whatever your task is. Now, we'll see what a machine learning workflow is, right? How do you start with a machine learning project? So the very first step is the data retrieval, right? So let's say I'll start with one example and then I'll explain each of these steps with that one particular example, okay? Let's say you want to perform, how do I go about? Okay, let's say you want to perform sentiment analysis on a given text data, okay? So let's say you have a lot of Twitter tweets, right? I give you about 1,000 tweets from 1 month's data, okay? Let's say I take the last 1 month tweets and I give you 1,000 tweets from it. And then I tell you that you have to tell me how many of these tweets are actually of the negative sentiment. That means they are talking about something which is, very negatively portrayed, or about hatred, or about anything that's negative, and you have to tell me how many of these tweets are actually positive. And this is your goal, right? So the first task is data retrieval, right? We'll have to fetch the data from somewhere. Let's say if we go ahead with tweets, then we'll have to capture the tweets from the Twitter website and then convert this data into a format that our machines can read, right? The second step that goes into the pipeline is your data cleaning and transformation, right? Now that you have all these tweets, let's say you have about 1,000 tweets, right? You cannot just ingest these 1,000 tweets as it is into your pipeline. You will have to do some pre-processing, some analysis, some kind of parsing and cleaning on it. So for tweets, for example, there could be a lot of noisy text, like a lot of people would have entered exclamation marks, emojis, those kind of information, which might not be very relevant, and you just want to do processing on text, right? Then in that case, you will remove all those extra information that's there. You will also do some kind of feature engineering, right? Those tweets are words. How will you convert these words into numbers, right? Your machine learning models are mathematical models, right? Mathematical equations, statistical concepts. So how do you, and it will only take in numbers as input. Any kind of data that you feed in, eventually it has to get converted into numbers. Whether you feed in voice input, you feed in text, you feed in images, you feed in video data, any kind of data that you feed in, it has to get converted into numbers first before it goes to your machine learning pipeline. So the conversion into numbers, and if you actually feed in a numeric data, then doing some kind of normalization or some kind of understanding of that data so that the data follows a certain mathematical distribution. All this kind of transformation and cleaning is very important, because if you just feed in garbage data, then your model will not be able to learn properly. The third part of the pipeline is your modeling technique, where you will have to train your machine learning model, right? This could be any kind of machine learning model. We'll look into some of the examples of machine learning models in coming slides. So this could be any kind of machine learning model, or in very simple terms, you can understand this could be a set of mathematical equations and concepts. So once you have your numeric input, you pass it through these mathematical equations and concepts, and you allow your model to train. Once your model is trained, right, you, with the first set, you might not have the best possible results, right? So you do some kind of multiple iteration, you try to change some values and then redo the training and kind of figure out a way to get best possible results. To get these best possible results, you will perform some sort of evaluation. So you have to evaluate how good your model is on a certain test set, which could be very similar to the kind of data that you have feed in for training. Once you perform this evaluation, now that you have created your model and your model is ready, you want to deploy your model, right? Because it is with you, let's say in a notebook or in a Python file or anywhere on your system. Now, from there, it has to go into actually whichever company you're working with, wherever that company's website or anything that's hosted, it has to go there and it has to actually generate predictions. So it can be used by your company's existing pipeline. So this entire workflow is the role of a data scientist or a machine learning engineer, where you have to start from retrieving the data, understanding the data, transforming the data, training a model, evaluating a model, and then actually looking into it that you rightly deploy your model. All of these steps are very crucial when you're working on a real office-like project. So now we'll start with what are the different types of machine learning, right? So there are three broader classifications: supervised learning, unsupervised learning, and reinforcement learning. So supervised learning is something where you have both the input and the target variables present, right? So these could be examples of tasks where you already know the output and you are allowing your model to understand the output and the input, and then making sure that it actually learns based on that, right? So you can actually look at it in a similar way that when, for example, whenever we used to go to school and we used to get homeworks, there could be, in some of the cases, we used to get some work in the class that was very similar to the kind of homework that we were supposed to get, right? The teacher used to tell us some examples of how we should be doing our homework, some examples with answers. And then based on that, we used to take decision that this is how our homework is supposed to be done, right? That it's the same analogy here. In supervised learning, you're giving the model few examples of input as well as the right output that you want your model to predict or generate, right? Then you give that data to your model, you tell your model that, see, look at this data, learn from it. This is your learning textbook or whatever. Now I'll ask you similar kind of question and you have to tell me the right answer for it. That is how supervised learning works. But in unsupervised learning, you do not give the model the actual output. Rather than that, you tell the model that, see, this is the data. I want you to generate patterns and insights and analytics out of this data. You have to just understand this data and tell me whatever you know about this data, right? This is how unsupervised learning works. Reinforcement learning is something where you train the model by a continuous feedback mechanism. So for example, in cases of models where you tell the model to do something and it performs an action, and then you give a feedback for that action. So if it does a wrong action, you give a negative feedback. If it does the right action, you give a positive feedback. Then your model will learn based on that feedback that whether it should repeat that action or it should not do that action and do something else. So this is how there are different kinds of machine learning. So today we'll go into details on unsupervised and supervised learning, and we'll see what are the different models that we can train within each of these brackets. So let's start with supervised learning. So like I said, in supervised learning, the machines are trained using labeled data. So you have your input data and you have your labels also. So if you can look in the image, you have your labeled data, which is your input data, which is just a collection of images. And you also have the labels available that what is the name of each of these image. Now you put this into your model and you give it a test data where you again give it some images, and your model has to tell you that what is the name of that image, right? So some of the real world examples of it could be image classification tasks, right? So for example, I tell your model to learn from a set of images, and I also give them the labels that these are the images of animals, these are the images of humans, these are the images of, let's say, nature, like this. I give it few categories and I tell the model to learn that, look at these images and learn its category. Now, when I give it a new image, I ask your model to say that which category does this image belong to. Fraud detection is another supervised machine learning use case where you allow the models to learn whether, based on the transactional data, a fraud has happened or not. So if you use a credit card, there are higher possibilities of credit card frauds happening these days. So in that scenario, you can actually give your model historic data where you give it all the transactional input, that where has this transaction happened, when it has happened, how much amount has been withdrawn, how much time did it take for this transaction, what was purchased, you give it all that kind of information. Based on that, and you also give it whether this transaction is a fraud or a legitimate transaction. Now your model will, based on this, your model will understand that which kind of transaction is actually a fraud. Now, whenever a new transaction comes in, if your model thinks that this transaction is very similar to a fraud transaction, then it will label it as fraud transaction. So like these, the supervised learning algorithm will map your input X to your output Y, and you have to give in both X and Y while training these models so that you can actually, allow your model to learn from this data. So supervised learning is broadly classified into regression and classification algorithms. So we'll see what each of these algorithms mean, what is classification and what is regression. We'll start by regression, right? So regression here also, because it's supervised, you have to give in the X and the Y values. But in regression, your Y values are continuous values. So like I said earlier, that let's say when you're doing the task of image classification, right? You tell your model to divide your image into different categories, right? Now those categories are not continuous values. That means if you have some 1,000 images and you want to divide it into 3 categories, then those are discrete values. Your images will only be either 1 or 2 or 3, like this, right? So then, because the output values are discrete, it's a classification task. You have to classify your data into different categories. But if you want to predict something, like for example, house price prediction task, right? That I give you some kinds of information about a given house and you want to predict the price of a house. So I give you that this house belongs to this particular locality. This has these many number of bedrooms, this much square feet area. It is furnished house. And I give you all of these details about a house. And based on that, you actually predict what is the right price of this house. So in those scenarios, you are doing a regression task. So for this regression, one of the algorithms that you can use is a linear regression algorithm. So in linear regression, what you do is you try to establish a relationship between a dependent variable y and an independent variable x. So x is your input data, which means for our house price prediction task, your x will be all of the different features that you have, right? So number of houses, the square feet area, the locality of the house, the number of bedrooms, everything, all those features about a given house, that will be your x. And then the price of the house. Let's say if the price of one particular house is, let's say, $2,000, then another house which is smaller, the price is $1,000. Some other house which is very huge is $500,000. So whatever the price is, I'm just making up numbers. So whatever the price is, this y will always depend on the features, right? You cannot just guess the price of a particular house. There has to be some reason as to why the price of one house is higher than the other and why the price of a given house is between a certain range or a certain number, right? So that reason we try to understand using linear regression, so that we make the model look at these features and we explain it to them that, see, if it is, so I'll give it multiple examples. Some examples I'll give it of, say, 1,000 square feet. Some examples I'll give it of 5,000 square feet, like this. And then based on that, it has seen the house prices. So now whenever a new house comes in for which you want to generate house price, it will see what is the square feet area. And based on that, it will make an assumption and it will decide that, okay, these square feet areas which are on the range of thousands have house prices between $2,000 to $4,000 or something. So this could be the possible number. So based on that, it decides your predicted value. So mathematically, how it's done is you try to represent it by an equation. Y is equals to a plus bx plus c, where a is your intercept, b is the slope of the line, and e is the error term. So this is like you're plotting a straight line, right? The straight line that you're trying to plot, that is the actual correct values. And you want to estimate the values of A, B, which are your hyperparameters. You want to decide the right values of A and B, so that whenever a new value comes in, let's say you get new values of X, right? I give you a new example, which has some 500 square feet, which has some 3 bedrooms. Like this, I give you new values of X. You multiply with this existing determined values of A and B, and you can get the new Y value. So it's just identifying these A and B values in the linear regression model based on the data that you have seen. So there are certain points that are to be considered for linear regression. So there has to be a linear relationship between the independent and dependent variables. And multiple regression suffers from multicollinearity. Multicollinearity would mean that if there are multiple features which kind of represent the same thing. Like, for example, if I have two features saying the number of bedrooms and the number of rooms. Now we obviously know that if the number of bedrooms are high, then the number of rooms will also be high, right? So these both are related to each other. So when you have features like these, then your model results suffer. So you should take care of multicollinearity and autocorrelation in between the features. So linear regression is also very sensitive to outliers. So when you have outliers in the example, like for example, you have about 1,000 house prices and one of them is very high, let's say $1 million. Then in that case, your model can, the A and B values can drastically change, and you should always take care of the fact that you remove outliers before processing your model. So multicollinearity can increase the variance of the coefficient and make them very sensitive to the minor changes. That means you have to make sure that multicollinearity is handled so that your model doesn't deviate way too much from what is the actual Y value. And okay, now another task that we do with house price prediction is your classification task. Let me just look at a few questions if there are any. How do we ensure that our data is clean enough to be given to a machine learning model? See, it's not like cleaned enough. It's like there are certain best practices that we usually follow for different kinds of data. So if it is a numeric data, then you have a certain set of rules that you usually follow. You look through data, you check through missing values, you check through outliers, you check through columns which are, categorical, or columns which are ordinal, columns which are continuous. You try to make them come under the same distribution. Then you normalize certain values so that values range between 0 and 1. Then you plot these values to see if there are certain absurd values in between or something. So that way you try to understand the data. So this is a complete task that you have to do. The data analysis task is a huge task that needs to be performed. Like for example, if it's text data, then you have to try to remove all possible forms of junk information, stop words, everything that comes under, so that you can eventually get clean and accurate, correct spelling text which you can pass to your model. Usually, how do you identify if it's best possible way is you follow all these standard guidelines and steps that you know of. See, data science is not something that you are given with a set of rules and you do it and you are done with it. It's a multi-iterative task, right? You go with a certain set of cleaning, you train your model, and you will see on your test data where it is working and where it is not working. Now, in cases where it is not working, there could be multiple reasons as to why it is not working, right? Your goal is to understand that why is it not working, right? So when you try to see why is it not working, if it is not working because of noise in your data, then you again go back, you try to make a few more changes, make your data more clean, and then repeat the same process. And if you don't know what to do again, you read through some of the existing researches and, you know, existing solutions that are available online that other people would also have tried on the same kind of data, what kind of feature selections they have done. So you keep reading and keep learning more and more techniques that can be performed to make sure your data is as clean as possible. What else? Is this also called an ML pipeline? Yeah, more or less your ML workflow is a machine learning pipeline. You can create a chatbot with your machine learning models. Multicollinearity affects certain models' accuracy. It does not affect all of the models. Some of the models are robust to it. You'll get to know in detail when you read about each of the different machine learning and deep learning models, which of the models are actually affected by multicollinearity. So your model will obviously get affected if you lose a large amount of data during all the cleaning and everything. So you have to make sure that you still have a certain amount of data, because machine learning models and deep learning models, especially deep learning models, you have to give a large amount of data for the model to be able to learn something correctly. Machine learning models can still do good with less amount of data, but deep learning models definitely need a very large amount of data. Okay. You want to know what is meant by pipeline. Pipeline is just something where you want to kind of like a complete workflow or a complete structure, right? Where how your models are trained, how it is designed, how do you render your models. It's just a complete workflow or a complete flow chart, or, you know, just understanding what these models are and how to run them. Okay, let's come to the classification task. Classification is basically dividing your data into fixed groups, right? So these are actual fixed numbers. So rather than dividing your data into continuous values like house prices, you're dividing into fixed categories. So now there are different types of classification. So there's binary classification, which means you want to divide your data into two categories, A and B. So like fraud detection, when you want to divide your data, whether that particular transaction is a fraud transaction or not, then it's just 0 and 1 label, right? If it is fraud, then it will be, let's say, 1. If it is not, then it will be 0. It's just two labels that you want to divide your data in. Multi-class classification, where you want to divide your data into more than two labels. Like, for example, I told you the example of image classification, where I give you images of nature, human, animals, plants, and then I'd ask you to divide it into 4 categories. Now, since this is more than 2 categories, it's a multi-class classification task. Then multi-label classification. Multi-label classification is where one data point, instead of going into one class, it can go into multiple classes. Like one example of this is when you actually watch a movie, right? If you see, movies are divided into genres. So one movie can belong to a comedy genre as well as an action genre. You would have seen a romance/comedy or action/drama. like this, there are multiple labels assigned to a particular movie. So that is a multi-label classification where you don't have a fixed label, but rather than that, you have multiple labels where your one data point can belong to. Imbalanced classification is a task where your data set is imbalanced. So in cases where one of the classes is way too high, your data for one of the classes is way high and the other is very rare. Like for example, cancer prediction task, right? Now when you have, when you want to decide based on your input data, clinical data, that whether a patient has cancer or not, you will only get very few samples of patients who actually have cancer, right? Because majority of the population does not have cancer. So that kind of task becomes an imbalanced classification. It's still a binary classification task, but the data is imbalanced. So we need to handle it in a different way. Okay, so this I have explained multi-class classification. So there are different applications of multi-class classification. So you get image classification, which I explained about, optical character recognition. Optical character recognition is a task of, identifying different numbers. So if I give you images of different numbers and tell you to decide which number it is, right? So in, like, for example, any of you who start to work with image data, you'll always start with MNIST data. So it is a data set of images of numbers ranging from 0 to 9, and you have to divide those images into 10 categories. Sentiment prediction task, where you want to decide multiple sentiments, which whether a particular text is, say, happy, sad, depressed, angry. Medical severity, whether a disease belongs to a low severity, high severity, but whenever you want to categorize it into more than 2 categories, it becomes a multi-class. All of these are real world applications of multi-class classification. So there are, again, about supervised learning, it can be used both for classification and regression. So like how we saw, linear regression is one of the models that can be used for specifically for regression tasks. Decision trees are one of the models that can be used for both classification and regression tasks, right? So decision trees in very simple languages gives you basic decision rules. So based on your training data, it will see that, let's say if the house prices are greater than this, then okay, the price should be greater than this much. If the number of bedrooms are less than this, then the price should be in this range. So based on your data, it tries to bucketize your house prices and tries to decide that whenever a new feature comes in, it tries to see that in between this, and this category where your actual data lies. So decision trees are also called as CART, which is classification and regression trees. The different types of decision trees: categorical variable decision trees, where you have a categorical variable, which is the classification task. Continuous variable, where you have a continuous variable, which is the regression task, right? So there are two major types. So how does a decision tree work? You have a root node. So your root node can be any one of the features, right? Let's say for house price prediction, your base root node can be the square feet area. So let's say if your square feet area is, you have multiple data points in your training data. Okay, you have some 1,000 data points in your training data. In those 1,000 data points, you will have different square feet areas. Let's say your square feet area ranges from about 1,000 to 5,000 in those 1,000 data points, right? Now, how will you split it? If you want to split it into 2 divisions, then what you can do, you can decide that if my square feet area is less than 2,500 square feet, it goes on the left side. If it is greater than 2,500 square feet, it goes on the right side. Now, when it goes on the left side, again, you use another feature. So then it becomes, if your square feet area is less than 2,500 and you have number of bedrooms less than 2, then it goes on the left side. Square feet area less than 2,500, number of bedrooms greater than 2, it goes on the right side over here, right? Again, on the right side, because it is greater than 2,500, then within it, the number of bedrooms less than 2, number of bedrooms greater than 2. So like this, you keep dividing it. And when you reach your actual value, wherever you want to stop learning it, you decide it's a terminal node. It's not a decision node, it's a terminal node, right? Then based on that, you decide and predict what is the right price of your house. So this is how decision tree works. To take the decision as to which feature can be your root node, we use concepts like information gain and entropy. And then we keep on splitting, we keep on deciding, and then to decide where to stop, we perform some kind of hyperparameter tuning. Random forest is another kind of supervised machine learning algorithm used both for classification and regression tasks. So random forest is just a combination of different decision trees. Let's say I give you some 100 decision trees, and each of those 100 decision trees have taken, and you want to classify your data into two values, okay, into two categories. So what your decision tree will do, it will see all of your features, and based on all those, if else decisions, it will decide whether your new data is in category 1 or category 2, right? Now, what random forest will do is, random forest will basically take the decision, it will design, let's say 100 decision trees, and it will take the decision from 100 different decision trees and take a majority voting. It basically combines different decision trees together, parallelly trains them, and then decides ki, okay, let's say if 70 of those 100 decision trees are saying it's class 1, then we'll go with class 1. Whatever the majority says, it goes with that. It works on the concept of bagging, also called as bootstrap aggregation, where you select for each decision tree, right? Now you have to train 100 decision trees. So for each decision tree, you can actually select which features you want to put in, and you don't have to give all the data and all the features to all the decision trees. You can give some of the features and some of the data to one decision tree, again, some of the features, some of the data to another decision tree. Like this, each decision tree can be trained on different features and different data. And then eventually all of them will give you some kind of combined output. And based on that, you decide that what is the right value for it. So as you can see from the image, we are training tree 1, tree 2, tree n like this separately. And you can see that each of these trees, there are different features, all these are different kinds of trees. It's not trained on the same data. If you have complete set of 1,000 examples and let's say 50 features, right? So what you can do is you can handpick, let's say 5, you select randomly 500 out of these, 500 samples out of this. And out of those 50 features, you select some 10 features. So now your new data becomes 500 cross 10. You give it to tree 1. For tree 2, you select, again, randomly select some 600 data points, and then select some 25 features. So then 600 cross 25, you give it to tree 2. So like this, you select features and select data points to give to different trees, and then whichever is the majority decision, you give that as output. Now again, the number of trees which are to go in, then how many number of features do you want to take into consideration? All of these are hyperparameters that you can tune. We'll look through, now we see which kind of models we can train, right? We can train a decision tree model, we can train a, let's say, random forest model, a linear regression model. But how do we evaluate these models? What is the right metric to decide how good our model is doing? Okay, what else? How machine learning is helpful for mechanical engineers. There are a lot of applications in mechanical engineering field as well for machine learning. You can actually image recognition tasks. It helps you in image recognition tasks. It can help you in text identification tasks. You can have a lot of research text on it, and you can actually design, and it'll help you. You can design a chatbot which can help you answer queries. So there are a lot of applications there as well. Yes, algorithms change for deep learning from machine learning. In machine learning, we have different algorithms, and in deep learning, we have different algorithms. What else? How to understand multi-correlation between the columns. So there are certain ways to actually capture multi-correlation. Like if you're working with Python, you can use the pandas library to figure out the multi-correlation between different features. And it will help, it will basically look at the data and see for how many data points these features are similar, and then give you a multi-collinearity value for you. Now you have, based on that value, you have to decide whether it's correlated together or whether it's not correlated together. Now for the evaluation matrix for supervised learning. Supervised learning, we have to divide our data into categories, right? And we already know the labels. So if you look at the image on the left-hand side, the actual positive and negative values are the ones which are the actual labels, right? So for a fraud detection task, whichever row has value 1, it will be actual positive. Whichever value has value 0, it will be actual negative. Okay. Whatever we predict from our model, that will be predicted positive and predicted negative, right? So true positive means that actually the value in the when I say actually, it means you already have the labels for the test set as well, right? And in when you look at those labels, so now you're matching your answers. Evaluation is in simple terms matching your answers, right? Let's say you have you have some answer sheet which is already there. So whenever you were given a homework, there's already an existing answer sheet, right? From where your teacher used to match answers and give you points on it. So now you are also doing the same thing. So if you have evaluated your model on say 100 examples, your actual 100 examples have some values 1, 0, 1, 0 like this, right? And your model has also generated or predicted some values 1, 0, 1, 0 for those 100 values. Now you want to match that for each of these 100 values, whether my model's value matches with mine, whether it's with the actual data or it does not, right? So if it is actually 1 and your model has also predicted 1, right? If it is both 1 and 1, then it's a true positive case, right? If your actual value is 0, but your model has predicted 1, then it is a false positive case. If your actual value is 1, but if your model has predicted 0, then it is a false negative case. And again, if both of the values are 0, it's a true negative case, right? So this is how we will label each of the values. So all these 100 values, you will label it with true positive, sorry, true positive, false negative, and true negative. You will label all of these data points, right? Now you will count how many out of 100 are true positives, how many out of 100 are, each of these values. Then you design these matrix. So your accuracy matrix. So this kind of table, right, that you see, a 2x2 table, this is called as confusion matrix, right? Where you design how many true values are there and how many true values you have predicted. So this left-hand side, the table that you see, that is confusion matrix that you design based on your matching values. How many are 1 and 1, 1 and 0, 0 and 1, and 1, 0 and 0, like this, you design this table. Then second number that you can, or second matrix is accuracy. So the formula for accuracy will be true positive plus true negative by all the values, right? So you want to decide out of all the values that are there, how many you have predicted correctly, right? So how many values, true positive plus true negative values, that means in both the cases, in 0 and 1, how many have you predicted correctly? Your precision and recall value. So precision value will be your true positives value by true positives plus false positives. So the first row, right? So true positives by the first row. So that means you want to decide that out of all the values that you have predicted, how many are correct. So try to sink in this line. Out of all the values that you have predicted, how many are correctly predicted? Okay. And recall is your true positive by false negative. The first column, which means out of all the actually correct values, how many you have predicted correctly, right? F1 score is just a harmonic mean of precision and recall. AUC, ROC, we'll look into the next slide. We'll see how AUC, ROC is calculated. And Gini coefficient and log loss is something which are calculated specifically for decision tree kind of problems. So this is for the classification task, right? Now for regression tasks, similarly, you kind of compute mean absolute error and mean square error, and then try different variations of these mean square error. So mean square error is nothing but, let's say your actual house price was 500, okay? And I have predicted some 300, right? Now there's a difference of $200 in between, right? So this is how you compute this difference, your actual minus predicted. Whatever is the difference you have, you find out the sum of the differences of all your values. This is one value, right? You will evaluate your model on some 1,000 or 100 values. How much difference is across all the values? So So your absolute error will be the sum of the differences for all those 100 values, right? Then you take the mean of it. So let's say your absolute error becomes some 5,000. Then you divide it by 100 because you have 100 examples. So your mean absolute error will become 5,000 by 100. Okay. Mean squared error means you square the error differences. So this 200, you will square it. Similarly, you square the differences and then you sum it and then you divide it by 100. Root mean square means you take the root of the value. So this is how you compute different kind of errors, and based on that you decide how good your model is. So AUC RUC is a performance metric for classification problems. So your true positive rate will be true positives. How many true positives have you actually predicted out of all the values? And your false positive rate will be how many false positives you have predicted out of all the values. So what we try to do is we try to define a curve which can be plotted between your true positives and your false positive values. And we try to find the area under the curve. So this curve that you can see, that is your ROC value, receiver operator characteristics, and the area that you can see, that is your AUC value. In simple terms, it will identify the degree or measure of separatability. It will tell you how good your model is in distinguishing between the two classes, right? So higher the AUC, better is your model in predicting class 0 as 0 and 1 as 1, right? So it means your model is very good with defining whether with which class is it and how correctly it has predicted it. So we completed the supervised learning classification and regression, and we also saw the evaluation matrix, right? Let's look at unsupervised learning. So unsupervised learning is, as I told you, when you don't have the labels for a data and you want your model to understand patterns from the data itself, right? So these unsupervised learning models are used for three main tasks: clustering, association, and dimensionality reduction. So some of the main reasons which describe why unsupervised learning is important is it helps you find useful information from the data, right? You're not even giving it any labels, you're just asking it to generate information from that data. And it works on unlabeled and uncategorized data. So it can work on large amounts of unstructured data. So in real world, you don't always have the corresponding labels, right? As I told you, labeling is a cumbersome task. So in those cases, unsupervised learning helps a lot. So some of the challenges that you can face is the computational complexity, because when it works on unstructured data and when you ask it to design patterns on its own, it will take a long time and lot of memory and lot of computation to come up with some decent patterns. Also, there are high risk of inaccurate results because you're not telling it or you're not giving it data to look into and say, like, look at this data and return the output. You're just telling it to understand the data on its own, right? Then there are more chances of getting inaccurate results. And the lack of transparency comes in when the data was clustered, because then you don't know that why a data point is clustered into a particular group, right? Because there is no output label that's given. So unsupervised learning is intrinsically more difficult. So there are three main usages of unsupervised learning, which is clustering, dimensionality reduction, and association. Now we'll look at the first major use case, that's clustering, where you want to divide your data into different clusters or different groups without telling the labels for each of these groups, right? So like, for example, I have a bunch of images of fruits over here and I want to divide it into different groups. So I want each fruit to go into their own groups. Now dividing data into each of these groups without labeling it, without telling it that this is an apple, this is a strawberry, this is a pear, without telling it. I'm just giving it and I'm just saying divide it or cluster it into its groups. So it has to look through its features. It has to see that, okay, this is red and this is round and this is red and this is not round and this is of green color. It has to look through its features. And based on that, it has to decide that, okay, which should go into which group. So one very regularly used clustering algorithm is the Kmeans clustering algorithm, where what you do is you divide your data into K groups, right? So you already tell the model that I want to divide my data into K groups. K can be any number, 3, 4, 10, anything. So I want to divide my data into 3 groups. Now you look at this data and you divide it into 3 or 4 groups, okay? So what it will do is First, it will look at the entire data. It will randomly pick. So let's say if you look at this image, right, it has to divide the data into 4 groups, right? So it will randomly pick 4 data points as centroids, right, randomly in the first pass. Then what it will do, it will try to find distances of each of the other data point from this centroid. And whichever is the closest will go into that group. So based on that, it will do the first pass of division. Now, because it has randomly picked these first centroids, obviously this won't be homogeneous, right? There will be some green values here, some blue values here, some red values here. Like this, it will be all mixed, right? Then it tries to change the value of the centroid so that all the correct values come in between. And based on that, it does its second pass. So if you look at this algorithm, it identifies the number of k values, then it measures the distance, and then it groups based on the minimum distance, right? So then what it does is it repositions the centroid. It keeps changing the centroid. How many times can it do it? It does it as many times as the clusters become stable. So when we say the clusters are stable, that means no more changing of centroid is happening. The distances are remaining same and the centroid is not fluctuating from its position. So it can go to multiple iterations and then it converges and then you can get your multiple clusters. There's another use case of unsupervised learning, which is dimensionality reduction. So when you have numeric data, you can have a lot of features, right? Let's say you have about 100, 200 features. And then it becomes difficult for your model to learn on those 100, 200 features. So then you want to reduce the number of features, right? So when you say you want to reduce the number of features, you want to perform dimensionality reduction techniques. So some of these are PCA, autoencoders, and singular value decomposition. All of these techniques are unsupervised techniques where so PCA is basically identifying principal components. So if you want to reduce the number of features to say 2 or 3, what it will do is it will try to identify the top 2 or 3 principal components in your data based on some probability distribution, and then it will reduce your number of features to 2 or 3. Unsupervised learning can be evaluated like how we saw evaluation metrics for supervised learning. This can also be evaluated using certain values like Silhouette score, where you try to identify the separation distance between clusters. So you try to identify that how these clusters are divided and how much is the distance between each cluster. Are the clusters mix and matched or are these different clusters? Then there's Kalinske-Harbaz index. There's also Davies-Bouldin index. All these determine, so Davies-Bouldin index determines the distance between in cluster and between clusters. So within cluster, how many, what is the distance in between the points, like how closely grouped are those points? And then it also determines that how much is the distance in between 2 different clusters. Again, RAND score determines the similarity between 2 clusters. So it will count how many pairs are aligned in the same cluster and how many pairs are aligned of different, belonging to different clusters, but they're coming in this particular cluster. So Jaccard score is also a method to identify the interaction of 2 label sets. So all these evaluation metrics help you decide that how good your clustering technique is and what features you need to change. So broader difference between unsupervised and supervised is that in supervised, you have your input data and your output data. In unsupervised, you don't have your labeled data. Supervised learning is simpler. Unsupervised learning is computationally more complex, and supervised learning will give you better results as compared to unsupervised learning. Okay, so now we talked about the modeling part, right? If you remember the ML workflow, right? We talked about the modeling and the evaluation part, right? We saw that what are the different kinds of modeling techniques, supervised learning, unsupervised learning, classification, regression, clustering. We saw all these techniques, right? And we saw how we can evaluate all of these models on the test data. Let's come back to the data cleaning and transformation part, right? And after that, we'll go to the deployment part, right? So data cleaning and transformation, there's this aspect where you want to select the right set of features for your data. One aspect is cleaning your data, right? When you want to remove missing values and you want to remove outliers and you want to clean your text, and if you have blurry images, you want to correct it. That is your data cleaning part. Another part is when you have multiple features, you want to select the right set of features so that your model learns it properly. So there are different techniques. that you can use to select these features. Okay, so let's start with filter methods. These filter methods, they can select the features from the data set. So these are irrespective of any machine learning algorithm. You can apply these for classification problems also, for regression problems also, for clustering problems also. You can apply these for any kind of algorithm. This is just on the input data, right? They are fast and inexpensive and are very good for removing duplicate features, redundant also, which are repeated features, correlated features. It can remove all of these features easily. So some of these methods are information gain, correlation coefficient. So as I mentioned earlier, right, multicollinearity can create problems with linear regression. So your correlation coefficient determines how correlated are two features to each other. So let's say if your correlation coefficient gives that feature A and feature B have a correlation value greater than 0.75, then you can actually remove one of those two features and then you can actually consider only one of those features. So you want to remove features which have a very low variance. When we say low variance, means all of the values for that feature for different rows is almost the same. So let's say I give you one feature, which is, let's say, the number of square feet areas of a particular house, and I give you 100 houses for training, and almost all of them have 1,000 square feet or 1,100 square feet. Then you won't be able to determine properly, right, that which has higher price and which has lower price if all of the features are same. So we try to remove those features where, you know, they have low variance, they are very similar to each other. We also remove features which are mutually dependent on each other in the case that if one value changes, then the other value also changes. So like this, you try to remove certain unuseful features basically. There are also techniques like wrapper methods. So wrapper methods, instead of looking into these statistical concepts that you look at correlation and mutual dependence and variation, you basically do an iterative approach. So what you do is you initially start with an empty set and you keep adding features and you look at the evaluation metric. So let's say you're training a XGBoost or a random forest or decision tree, right? You have 50 features. You start with 0, you keep adding features and you keep noting down the accuracy. Whichever number of features give you the highest accuracy, you select those many number of features. Backward elimination is also the same. You start with 50 and you keep removing, and wherever you get best number of features, you stop there. Bidirectional and exhaustive selection is again the brute force. You apply both forward selection and backward selection there. So these are certain techniques, but remember that wrapper methods are time consuming tasks because you have to look at all the features one by one. So this will take a lot of time and computational complexity. There are also embedded methods. So embedded methods can take care of the drawbacks of both filter methods and wrapper methods. They are more accurate and they take into consideration the combination of features as well. So there's a regularization technique where you try to add penalty to different parameters to avoid overfitting. So there's something called as lasso and lasso regularization, where what you do, let's say you are training a regression model, right? We have seen earlier that there was this error term that gets produced, right? So you add a penalty to that error value. Now, when you add that penalty and you backpropagate and you change the values of A and B, it can be possible that for some of the features, when you multiply those A and B values, the features become 0. So then you remove all those features whose coefficient becomes 0, and then which are not useful when applying this penalty value. Tree-based methods are also useful. Like for example, in random forest, we saw that by bagging, we can actually selectively pick some features. So, okay, now that we have done feature selection, we have done modeling, we have done evaluation, okay? Let's say your model receives an accuracy of 50%. What will you do? Your model is not doing good. You know it's not doing good, right? So there are certain techniques which you can use to again retrain the model to get better results. So cross-validation is one such technique. What cross-validation does is you have to divide, let's say you have 100 examples that you're given into training, right? Initially, what you will do, let's say you do a 20% split, you train it on 80 examples and you test it on 20 examples. And on those 20 examples, it gives you a 50% accuracy. So rather than doing training and testing split like this, what you do is you take all these 100 examples and then you try to divide it into different groups, right? So you have to divide these 100 examples into 5 groups, right? And then each time one particular group will be used for testing and rest of the group will be used for evaluation, training, right? So this is a k-fold cross-validation technique where each of these fold is called as the groups, and k means the number of groups into which you want to divide it into. So let's say I use a 5-fold cross-validation technique where what I do is these 100 examples, right? I have to divide it into 5 groups. So I have 20, 20, 20 like this. I have 5 groups. Now what I'll do, I'll pick the first group. I'll evaluate my model on this first group and I'll train on the rest 80, right? Then I'll pick the second group. This will be used for testing and the rest 80 will be used for training. Like this, I do the training 5 times. And whichever model gives me the best results, I select that model for my accuracy numbers. So this prevents overfitting because your model is trained and tested on all these groups. And it gives you better model selection parameters. There's also one more technique, which is leave one out cross validation. So this leave one out cross validation technique means that you want to leave one value out and you want to train on all the rest of the values. Earlier, we divided into 5 groups, right? And we wanted to train our model into each of these, based on each of these groups, right? So that means one group is for testing and rest 4 groups are for training. Here, we just remove one sample. So 99 we use for training, 1 for testing. So we repeat this process 100 times because we have 100 data points. So what happens is this results in low bias because we are considering all data points for training and for testing, but high variance, because what will happen is if you leave out a data point that is an outlier, then your model parameters will fluctuate very much. Also, this model will take longer to train, obviously, because you want to train your model 100 times. So in k-fold cross-validation, you are just training your model 5 times, right? Because it's a 5-fold cross-validation technique. But in leave one out, you're training your model 100 times because each time you leave one data point and you train on the rest of the models. There's also another technique called as stratified k-fold validation, where instead of random sampling, like when I said that you want to divide your data into 5 groups, right? So how does which data goes into which group? How do you decide that? So one you can do is randomly divide it into 5 groups, right? So maybe you have your table and then you just take the first 20, then next 20, then next 20. You don't decide on any logic that these should come together and these should come together. That is your simple k-fold cross validation. But when you actually decide on some logic that, because these have this feature is similar, so they should come in one group. This other set has this feature similar, so this should come in one group. When you group it based on some logic, then it becomes a stratified k-fold cross validation. So we have looked into cross validation technique, which is one of the techniques to improve your performance of the model, right? Because it will avoid overfitting and also underfitting. It will help you select good parameters and it will make you decide that if your model is doing good on the training data as well as on the test data, right? Another technique with which you can actually improve your performance is hyperparameter tuning. So hyperparameter are basically all the parameters that you can change which can actually control the performance of the model. So for example, in a decision tree classifier, there are certain parameters like criteria. So when I say criteria, it means based on which criteria you want to decide which feature goes in first, right? You can use information gain to decide which can be the root node. You can use entropy to decide which can be the root node. There's also another feature called as max depth, parameter called as max depth, which means how many number of times do you have to keep on splitting, right? Where do you stop with the decision tree? So all these numbers, right, or values or whatever, these are tuned. That means you can change these values. Like max depth, you can keep on changing. You can change it to 3 to 5 to 10. You can change these values. And then based on that, based on your data, you can decide the right set of parameters. There's also some other examples could be like, for example, a support vector classifier. There's a kernel where you can decide whether you want to divide it based on a linear kernel or you want to divide it based on a non-linear kernel like RBF kernel or some other kernel. Just give me 1 second. Yeah. Okay. So there are few steps that you can use to tune or change these hyperparameters, right? One, you select your base model, right? So whichever is your base model, let's say you want to do it for decision tree. So now you have selected decision tree and you know that these are the 4 or 5 parameters that I want to tune. And you also have multiple options. So for example, in decision tree for criteria, you have options to choose between entropy and information gain or log loss. Then in the max depth, you can choose between range between, let's say 2 to 20. Then some other like this, you decide all your parameters and you decide it's either it could be category or it will be a range, right? So you decide the category and range and everything. Then you have to identify the right searching method, which you can use to search that which hyperparameter will give you best accuracy or best result. And then you apply cross-validation and test your results. So there are different search techniques, right? There's something called as grid search. What it will do is it will look through all possible combination of hyperparameters. So let's say you have 2 hyperparameters like criteria and max depth. And max depth ranges from 2 to 20. So that means you have 18 values for it. Okay. And criteria ranges from information gain and entropy, 2 values. So then how many combinations that you can form out of it? So for each criteria, you have 18 max depth values. So you have almost 36 possible, combinations, like 36 possible values that you can test out of it. This is just for 2 hyperparameters. In real case scenarios, there are multiple hyperparameters to tune and multiple values. Like your max depth can range from 2 to 100 also, or 1 to 200 also. I'm just giving you an example. So now that you have these 36 possible values, you have to choose which one of these will be the best possible value for your result. So what you will do, each time you'll pick one out of this 36, you'll train your model, you'll see how much accuracy you're getting. Then you'll repeat this step. Whichever combination gives you the highest valuation, you go ahead with that kind of computation technique. Obviously, this is very high on computation, it takes a lot of time because only with 2 parameters and just with 18 values, it's 36 times. If you have 6 parameters, each ranging into hundreds of values, it will take a lot of time to do this. Other than doing grid search, there's another technique called as random search. So in random search, instead of looking through all possible parameters, it will randomly pick few parameters from the grid space and then try to optimize that. So you can use randomized search CV technique to perform this. There's also a technique called as Bayesian optimization. So there's a hyper-op technique that you can use. Here what you do, you create a probability model. So this is a mathematical probability model, and then you decide an objective function. Objective function can be anything. It can be as simple as a sin x curve. So then what you do is you find the hyperparameters that best fit this objective function. And then based on that, you decide that which of these hyperparameters give you the best possible results. So this is how you perform a Bayesian optimization. So based on certain models, so there are certain known experiments that, these hyperparameter search techniques work with these kind of models. So based on that, you can actually select the right model and you can select the right searching technique and then perform cross-validation. Okay, before we go into deploying, let me see. By 20%, how can we predict the accuracy of the whole data? So you don't predict the accuracy of the whole data. There are 2 different metrics, which are the training accuracy and the testing accuracy. So 20% is just your test set, right? So you get the test accuracy on that 20%. And then on 80%, you get your training accuracy, right? When I say your model is overfitting, that means what will happen is your training accuracy will be very high and your test accuracy will be low. So if your training accuracy is, let's say, 95%, but on the test data, you are only getting 70%, that means your model is learning way too much on the training data. You have to control that learning. So you actually determine the accuracy on all the data, and then there are different parameters to understand. Okay, so this is done. Skills required for freshers. So basic skill set is just you have to go through the entire theory of machine learning, if possible, deep learning, Python. You have to understand, I think with Guvi course, as it has been explained, you will get to know all of these techniques. You'll learn with projects, you'll learn everything there. And then you have to also apply them in practice. You can do certain machine learning projects. You can have your own, you can open your own GitHub repo and keep on putting projects there. You can do projects that are given by Guvi. And based on that, you will be able to, learn. So you have to get your theory right. That if I ask you a question that why my model is overfitting, and if it is overfitting, what will you do to make the model work properly, right? So because what happens is people think that machine learning just means training your data, but it's not that. It involves a lot of different aspects to it. Even data transformation is one of the major fields that comes under machine learning. If you don't know how to rightly transform your data, your machine learning models will never work, and you will not be able to understand why it is not working. The main problem is understanding why it is not working. Only then you'll be able to correct it, right? So parameters, you can have a lot of different parameters for different models. Hyperparameters are just those parameters which you can change, which are tunable. Okay. I've already explained how to choose the right parameter. Prerequisites for image processing, such as image classification, recognition, which libraries are useful. So there are different libraries, right? Usually image classification recognition is done by using CNN models. Now these are deep learning models, right? Before that, you have to perform some kind of image cleaning. So you have to use different kinds of image cleaning libraries where you can actually remove blurry images, make them into right set, standardize them properly, augment the data. So there are different kinds of libraries, numeric libraries, which are used on top of that. Then you can plot your data. You can see your images, how these pixels are aligned. So you can use matplotlib kind of libraries. Then you can use CNN libraries for training your models. And then because it's a classification task, you can use sklearn majorly for all the evaluation techniques. What is the process of finding multicollinearity? You can find, let's say, if you have a table, you can upload it in the form of a data frame in Python, and then you can perform multicollinearity setup in the Python data frame. There are techniques to identify multicollinearity between the different columns of a data frame. What is the range? So this multicollinearity feature, right, the correlation coefficient, that ranges between 0 to 1. So that means if it is very close to 1, that means those two particular features are highly correlated. So if you have 50 features, you will get 50 cross 50 table or data matrix, where each values will be the correlation between each of these features. So features correlation with itself will always be 1, right? Because it is always correlated with itself. So the diagonals will always be 1. And then whichever values are very high, you can look at the heat map. If you Google a correlation heat map, you'll be able to see some images where you can identify that if it is very highly correlated, those heat maps are darker in color. And then based on that, you can eliminate those features. I don't know what you want to do. You want to understand what CNN and Keras is? Like, please reply your question properly. Okay, let's go back to deploying machine learning models. Now, if you remember that ML workflow, we are done with data feature selection. So in the data transformation, this part was feature selection. We have looked through modeling techniques, supervised and unsupervised learning techniques. We have also looked through evaluation metrics, and we've also looked through retraining, like how do you do cross-validation and hyperparameter tuning. Now the next step that comes in is your deploying. You have already built your model. Your model, let's say, gives you 90% accuracy on your test data. You have tested it all. Now you want customers or whatever projects to use your model, right? Because that model, when you run, so when you do any kind of coding or anything, how do you do it? It will be present either in your system, right, your computer, or it will be present in some let's say if you're using AWS, if you're using Google Cloud, so it will be present in some cloud server, right? From there, how do you make sure that real-time customer data you can take input real-time customer data, you can generate predictions, and you can return it back. So that is the process of deploying these machine learning models. So you have your machine learning model somewhere. You have to integrate with a web framework, right? So your company can already have a website, right? So you have to integrate with that web framework, and then you have to deploy your model to a particular server. So from which server, your web framework will send an API. It will call that model, it will get results, and then it will show it on the UI, right? So your server can be AWS, it can be Microsoft, Heroku, Google Cloud, can be any server based on whichever your company uses. So certain things that you need to consider before deploying is how good your reproducibility is. That means that you have collected the data, you have done some transformations, and you have checked your results, right? If somebody else repeats the same steps, right, based on the code or based on your model, if let's say you have tested this data on some 100 examples, if somebody else goes ahead and tests it on some different 100 examples, it should not happen that they are getting a 20% accuracy or a 30% accuracy. They should also be getting similar accuracy. So this reproducibility on another data is very important. How good your model stages on retraining and reevaluation. So your code should be of that format that your model can easily be retrained and reevaluated at different stages and different versions. Like, okay, let's say today you train a sentiment analysis model on tweets. I give you 1,000 tweets from last month. Okay. Now you deploy this model. 6 months down the line, those 1,000 tweets which were from June might not be as relevant. Like the world keeps on changing, right? Things keep on changing. So maybe last month the tweets were more about whatever floods that are happening across India and everything. 6 months down the line, there could be some other problem that's happening. So you want to take into consideration and you want to keep retraining your model. So that means your code and your entire pipeline should be very smooth, that you can just bring in new data, and everything that you have done for the old data can be easily automated. You don't have to repeat those steps manually. Auto scaling. So let's say you have deployed the sentiment analysis model. Now it's been 2 years, and now you have a lot of tweets with you. Earlier you started with only 1,000 tweets, but now you have 10,000, 15,000 tweets. So your model should have the capability to be able to train and evaluate on larger sets of data. Stress testing. That means you're checking out all possible corner cases before deploying your model. That means, let's say you checked for some majority of the cases, but you missed out on some aspect where, let's say there was a sarcasm in a tweet and you missed out on that aspect. And now if such tweets come in, your model gives out wrong predictions. So stress testing is basically checking out all possible corner cases and monitoring data drift. Like I said, 6 months down the line, the data could actually change. Those tweets could be about a different topic. So when data drift happens, when your data keeps on changing, you have to be able to retrain your model. So all this should be taken into consideration before you deploy a model. Your model should be very reproducible. It should be able to retrain and evaluate very smoothly. All the steps should be automated. Like it should not happen that 6 months down the line, if some other team or some other project picks up your model and they want to use your model, they're just debugging the code and they're not able to train it and not able to get any accuracy. So ML ops is a machine learning ops technique which helps you do all of this deployment, right? So it will help you perform all of this automatically. So you can do the data preparation, you can do the training, you can do the monitoring, deployment, and you can automate your model retraining, right? That means once you have done the first 3 steps, the data preparation, training and evaluation, deployment, then it will keep on monitoring your data. So let's say today you have deployed your model, right? Now for continuous next 1 month, you have to keep monitoring the performance, that how is your model doing? And if needed of retraining, then all the steps that you have done right now, there has to be an automated script that can rerun those steps. So this then makes easy deployment of your model. So this helps with continuous integration and deployment. So the primary benefits are efficiency, because then you don't have to manually do all of those steps again and again. Scalability, If everything is automated, it will be easier to repeat those steps on 10,000, 15,000, and even larger data points, and risk reduction. Okay. Sorry. Now that we have seen different techniques and the complete workflow, that how do we do data transformation, how do we train our model, how do we evaluate a model, how do we tune our hyperparameters, how do we deploy our models, we can see what are some real-time applications. So machine learning is used across many applications, like it's unlimited. These are only some that I've picked, which are very common so that everybody can relate to it. So image recognition is one that I've already explained. Then one application is automatic speech recognition. So you have all these devices at your home, right? Google Home, Alexa, Bixby, Siri. When you say something, it actually recognizes your voice, listens to what your question you're asking, and based on that, it decides what answer to give. If you just say, Alexa, what time it is, it will listen to that question and it will give you the answer of what time it is. So that means it is listening to your speech. And in the backend, it is converting your speech into first text, right? That conversion of speech into text is automatic speech recognition. Now that it is converted into text, so you have a text of what time it is, it will pass it on to some chatbot. So those chatbot are virtual assistants, right? That chatbot will decide that, okay, it will understand that what is the question. And then it will say, okay, now I have to tell what the time is. So it will look at some clock API or something. It will return the time. And then that time will be returned by Alexa in terms of voice only. So this entire speech recognition and virtual assistant workflow is done by machine learning. It also performs speech translation. So you can see Google Translate, right? Where you just type in information from one language and it converts it into another language. So that uses machine learning. Sentiment analysis, where you want to, all these customer feedbacks, right? If you go on Amazon or any other e-commerce platform, for each product, you can see the review. And then after that review, you can actually see the sentiments which are negative and which are positive. So basically deciding which sentiments are positive and which sentiments are negative. Then what, in some cases, like for example, in Flipkart, in some of the cases you can see, they also highlight the features, the positive features and the negative features of a given product. Like they'll highlight that the display of this phone is good, the battery of this phone is good, but let's say the anything else, right? The camera of this phone is bad, like that. So they'll highlight certain features. So that highlighting is done via sentiment analysis. Then again, self-driving cars is one such application which uses reinforcement learning. You would have read the news that Tesla has come up with self-driving cars that has been tested in US. So that uses reinforcement learning, object detection, that uses image recognition, that uses a lot of combination of a lot of machine learning algorithms to decide when the car has to go right, go left, stop, make a turn, everything. Medical diagnosis, it looks through the past history and based on that decides whether a patient has a certain disease or not. Email spam prediction, or even message spam prediction. Then it also has applications in search engines. Like if you search anything on Google, right, it will return you the top 10 or top 20 relevant answers to it. Like for example, if you search about the World Cup, it will give you the top 10, top 20 links which talk about the World Cup. So how do you result in these links, right? There has to be some similarity module where whenever you type in a question, it looks at the embeddings of the question and it looks at the embeddings of the existing data and then matches it and gives you the one that matches completely. So that there we use a machine learning algorithm. Product recommendation. So on Amazon, you might have seen that whenever you buy something, it also suggests that customer who bought this also bought this. So there you use machine learning algorithms. Stock market price prediction and weather forecasting, which uses time series data. So time series information to actually determine what the future price will be. All of these are very basic real-time applications that a lot of you would have used. There's also face recognition that's available in our phones, right? We usually unlock our phones with our faces. So there also, the face recognition app, what it does is it captures an image of your face and then it matches it with the existing saved image that you would have initially registered. And if it matches, then it returns, it unlocks your phone. If it doesn't match, then it doesn't unlock your phone. So that way, whenever you use any of these applications in real life, you're using machine learning or deep learning in the backend. Now we look at a real life case study, which is a credit card fraud detection. Okay, we'll see what steps to apply to get to the result. Okay, so credit card fraud detection can be explained as criminal deception, right? With the intent to get financial gain. That means frauds can happen two ways, either by faking an identity online or by doing stealing cards. So how are these frauds recognized? So there could be certain features which tell you that this is a fraud. The features could be, it could be a different location, right? That means usually you use your credit card at a particular state. Let's say use your credit card in Bangalore or Chennai. But now this fraud has happened somewhere in the north or somewhere else, right? Then there could be a different buying pattern that usually you use your credit card only for 1,000 rupees or 2,000 rupees. But this time, this credit card transaction has happened for 50,000 rupees, like that. So there could be a higher amount or a higher frequency of purchase. For example, someone is using your credit card to do 10 purchases on a single day, but you don't usually do that. So that way you can actually identify which of these transactions are fraud transactions. So what is the challenge with this data is, this data is highly imbalanced because fraud doesn't happen every day to every customer. If you have thousands of transactions, even if you take the data for 1,000 customers over 1 year, you will have millions of transactions, right? Out of those, there could be 1% or 2% of the times when there is a fraud happening, right? Now, because this is a highly imbalanced data, there can be two possible techniques. One can be imbalanced binary classification. Another can be an outlier detection task. Two ways you can actually determine fraud. Now, one, because this is a highly unbalanced data, you have to handle the data first. So what you can do is you can try to make the data slightly more balanced. So there are certain techniques to handle imbalanced data. Like, for example, you can perform sampling. So you can oversample your data. That means 1 or 2%, you can actually duplicate that data so that it becomes slightly higher. You can also do a synthetic minority oversampling, which is a smart oversampling technique. You can also reduce the majority class. And then you can experiment with different classifiers, because let's say we go ahead with binary classification. So once we have slightly balanced the data, we can go with something like KNN, naive Bayes, and even balanced Bayes classifier. These are some of the classifiers that work well with imbalanced data. Then for evaluation, you cannot use accuracy, right? Because accuracy will give you the total number, true positives plus true negatives. And your true negatives will be so high that your true positives will get undermined. Like, for example, even if you evaluate it on 100 transactions, and out of that only 2 are fraud, right? And 98 are legit. Out of that 98, if you're able to predict 95 correctly, and out of that 2, if you're not even able to predict any of them, then also your output value will be 95 by 100. So it will be 95% accuracy, right? But actually you're not predicting fraud at all, right? So that means your accuracy is a bad value to go ahead with, right? So instead of accuracy, you can check for precision recall for the minority class, that how good are you doing for the minority class. And you can also check for AUC values in case of imbalanced data.